Okay, so today we're going to look at single replacement reaction. So if I haven't mentioned it before, we abbreviate reactions RXN. Just saves a couple of letters there. So there are several things that make single replacement reactions a little bit different than in previous reactions we discussed. Let's look at the typical form for a single replacement reaction first, how we recognize what it is. Typically a single replacement reaction will look like something like this. So you have a compound plus a single atom. Okay, so we recognize combustion because you had the addition of oxygen gas. We recognize synthesis because it had two reactants and only one product. We recognize decomposition because it only had one reactant. So we'll recognize single replacement by this form. We'll have a compound plus a single atom or a diatomic molecule here. So one of the interesting things about single replacement reactions is that all proposed reactions won't actually happen. Okay, they won't proceed. So in synthesis and decomposition and combustion reactions, we just assume the reaction happened and we followed the rules to predict the product. So with single replacement reactions, we're going to have to take a few more steps to see if the reaction actually happens. So for single replacement reactions, no reaction is a perfectly valid answer that we will have to use sometimes. So the tool that we'll use to determine if reactions actually happen will be called the activity series. So if you go to I believe the next page in your notes, you'll see the activity series, and it has quite a few elements listed out horizontally. So starting from the left, you'll see lithium, rubidium, potassium, barium, strontium, calcium, and so on, all the way to the right where you have silver, platinum, and gold. You'll often see the activity series listed vertically, so if you see it listed vertically, don't be confused by that. So what the activity series does is it tells us the reactivity of these metals, so how reactive they are. So you'll also see it labeled the reactivity series occasionally. So the way we read it is on the far left we have the most reactive molecules. So you'll see that the most reactive molecules are typically alkali metals with one or two alkaline earth metals thrown in. And on the far right, we have the least reactive metals. Okay, so the least reactive metal listed here is what we consider to be the precious metals. Okay, what you would typically make jewelry out of. The reason that these metals are so valuable and so preferred for jewelry is because where they lie on this activity series. Okay, you don't want to buy a piece of jewelry and have it react with the moisture coming from your skin in the form of sweat. Okay, so you don't want a metal that's going to react with water very easily. So because these metals are very unreactive, they make good metals for jewelry. So let's look at how we use this. Okay, so let's go ahead and jump in to an example and then we'll learn how to use the activity series to help us find an answer. So you also see in the notes there's a little graphic where you have a little couple and another guy comes in and kind of breaks up the couple and another couple forms. So that's kind of the general form for the single replacement reactions. The single atom comes in and replaces one of the atoms in the already formed compound. So there are four categories of single replacement reactions that we'll discuss, but the first category is by far the most important and by far the most common. So let's go ahead and jump in and look at metal replacement reactions. So I could look at, I'll label it, we have lithium solid plus, we'll say FeCl2 AQ. So that means there's a solution of iron 2 chloride. So now we say, does the reaction happen? Okay, and if it does happen, what is the product? So essentially, if the reaction happens, let's go ahead and just assume the reaction happens first and write the products. If the reaction happens, the lithium is going to replace the iron and bond with chlorine. So how do we know that the lithium doesn't replace the chlorine and bond with iron? We could write in the charges here. Iron will be plus 2, chlorine's minus 1, okay? Lithium's plus 1. So we know the plus 1 doesn't want to pair with the plus 2. The plus 1 wants to pair with the minus 1, okay? So I can write this together. LiCl. So I have plus 1, minus 1, so I'm in good shape. And then I have iron left over. Okay, so iron's left over by itself. So typically the single metal that's left over will be a solid and the compound that's formed. Okay, we'll say it's an aqueous solution there, but we can just leave these off for now. Okay, let's worry more about getting the products correct now, and then we'll go back to that later. Okay, so we can go ahead and balance this. We can say 2 there, 2 there. So now we're balanced. The lithium came in and replaced the iron in the iron 2 chloride atom. So that's how we would write the reaction, but we skipped a major step. We have to ask ourselves, does this reaction even happen? Okay. So for the reaction to happen, lithium has to be more reactive than iron. It has to be reactive enough to come in and replace it. So for a reaction to happen, the single metal has to be more reactive than the metal in the compound. So let's go to the activity series and check it out. So looking at the activity series, we have to ask, is lithium more reactive than iron? So another way to say it is lithium further left on the activity series than iron? And we see that it is. Okay. So because lithium is more reactive than iron, this reaction actually happens, and that's my final answer. Okay. So let's go ahead and look at another one. Let's look at zinc metal plus magnesium chloride. Okay, so in the previous example, we went ahead and wrote the products first. That was just kind of to give you an idea of how we write the products. Really, we should go ahead and see if the reaction even happens first, because if it doesn't happen, then we don't have to do the work of predicting the products. So let's go to the activity series and see. So for this reaction to happen, zinc has to replace magnesium. Okay, so zinc and magnesium need to switch places. So if zinc is more reactive than magnesium, the reaction will happen. So if we go to the activity series, find zinc and find magnesium, we see that zinc is not more reactive than magnesium. It's further right than magnesium. So because it's not more reactive, the reaction will not happen. Okay, so when you mix these two together, nothing happens. So a couple of ways to show this. We can write no reaction as the product. I typically abbreviate it capital N, capital R. Okay, there's no need to write out the products. Let's say, for example, you had gone ahead and predicted what the products would be. That's okay. Just go back and put an X over the arrow. So if you do write the products out beforehand, an X over the arrow shows that the reaction doesn't actually happen. Okay. So let's look at another one. Let's look at Ca plus CuCl2. And I won't worry about the phase symbols here. So we have to go in and ask ourselves, before we worry about predicting the products, does the reaction happen? Is calcium more reactive than copper? So I go to the activity series, you see that calcium is further left than copper, so I see that the reaction does actually happen. So I can go ahead and predict the product now. So I need to decide, calcium's obviously going to react or do the replacing here, and you should recognize that that calcium will replace the copper. We consulted the activity series for that. But if you forget which molecule to which atom to replace, you could write in the chart just +2 - 1. You know that the positive calcium is going to pair with the negative chlorine there. So I'm going to write the product CaCl plus, I have copper left over. I check my charges, +2 - 1. I cross them. So now I'm good to go here. I'm already balanced. Okay. So this is the typical form of single replacement reactions. Okay. You'll see a metal plus an ionic compound, and you'll have to ask yourselves, does the metal replace the metal in the compound? So ask yourself, is it more reactive? And obviously the activity series will be something you'll always have as a reference, so you won't have to memorize that. Okay, so just don't forget to consult it, and don't assume that the reaction happens, because no reaction in a lot of cases is a valid, or more than valid, is the only correct answer. Okay. So another major form of single replacement reactions would be a halogen replacement. Okay. So we would have a compound containing a halogen. So remember, the halogens are fluorine, chlorine, bromine, iodine, and astatine, but we really don't encounter astatine, so we won't worry about that. So one of those comes in and replaces another one. So if you'll notice at the bottom of the activity series, we have the halogens listed out. Okay. So on the left side is the most reactive halogen, and on the right side is the least reactive halogen. Notice astatine is not even listed here. Okay. So fluorine is most reactive and iodine is least reactive. So let's go ahead and look at one of these. So I can have NaCl plus F2. Okay. So here you see there's no metal, okay, that's trying to replace another metal, but we do have the general form, a compound plus a single atom. Fluorine is not a single atom. It is two fluorines bonded together, but it is a single element. Okay, so we still consider that to be the same. So now we ask ourselves, is fluorine more reactive than chlorine? Go to the activity series. You see that F is further to the left than chlorine, so it is more reactive, so it will replace the chlorine. So remember, you always write the metal first. So I have NaF plus chlorine. Okay, so I have the chlorine left over. Remember, chlorine is special. Chlorine's diatomic, so I have to make it Cl2. Then I have to balance my reaction, a 2 there and a 2 there, and I'm good to go. So let's look at another one. The same typical form. You have NaF plus I2. Okay, so you want to work smart, not hard here, so go ahead and see if the reaction even happens before you write the products out. So if I look at the activity series, for this reaction to occur, iodine would need to be more reactive than fluorine. We see on the activity series that is not true. Okay, so iodine is not reactive enough to replace fluorine in this compound. So we can just write capital N, capital R, no reaction. Okay, so these are the two most common forms of single replacement reactions that you'll see. Just be sure to always use the activity series when you have these types of reactions. So now let's look at two more kind of specialized cases of single replacement reactions. For the next one, we're going to combine numbers 3 and number 5 in your notes. So for number 3, this is the replacement of hydrogen and H2O by a metal. So if you look on the activity series, hydrogen is actually listed on the activity series. Okay? So we treat it somewhat as a metal here because it will have a positive charge, so it can be replaced just like a metal can be. So let's look at an example here of what this might look like. So I might have something like Na plus H2O. Okay? So this one is probably a little bit more difficult to immediately realize it's a single replacement reaction. But when you see a single metal plus water, you should think about, okay, this is automatically a single replacement. Another way to write this that might make it easier to see is I could write sodium plus HOH. Okay, so then you have a hydrogen with a hydroxide. So that might make it easier to see the single replacement reaction that's going on. So now we have to ask ourselves, can this sodium replace this hydrogen? For this single replacement reaction to happen, sodium needs to be more reactive than hydrogen. So I go to the activity series and I check, is sodium further to the left than hydrogen? Is it more reactive? Yes, it is. Okay. So in this case, the sodium will come in and replace this hydrogen. So I have Na, and then I'm left with this, OH. Sodium hydroxide. And then this hydrogen got replaced, so I have an H left over. But hydrogen is diatomic. Okay? So I can't forget to put that H2 at the end there. Okay? So now I see that I have the typical form of a single replacement reaction. It's just a little bit different because we write H2O in this form. If you go ahead and write it like this, it'll be easier for you to see. So now I keep forgetting to go back and balance. Okay? So I have the correct number of sodiums, I'm good there, the correct number of oxygens, but my hydrogens are off. I have 2 hydrogens over here and 3 hydrogens over here. So to go back and balance my reaction, I can put a 2 there, I can put a 2 there, I can put a 2 there. So go back and double check, 2 sodiums, 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. I'm in good shape now. Okay? So really, this third and fifth class of reactions are the exact same as the first class. Okay, so don't be thrown off thinking it's something different. We just listed it out separately so you would be able to recognize when you see a metal plus H2O, you have to recognize it's single replacement. The metal just replaces the hydrogen. So let's look at one more. Let's look at PT, platinum, plus H2O. And I'll go ahead and rewrite it as PT plus HOH. So I'm asking myself, is platinum more reactive than hydrogen? So can platinum replace hydrogen? So I consult the periodic table. I see that platinum is less reactive than hydrogen, so it can't replace it. Okay? So because of that, I have no reaction. Okay? So platinum is not reactive enough to replace hydrogen there. So I get no reaction. The last type of single replacement reaction that we'll see is when a metal replaces the hydrogen of an acid. Okay? So let's see something like this. So we'll see Na plus HF. Okay, so the same basic concept as above. We just have to ask ourselves, is this sodium reactive enough to replace this hydrogen? You look at the activity series, you see that sodium is further to the left. Okay? So because it's further to the left, sodium is able to replace the hydrogen. Okay, so I always write the metal first when I write an ionic compound, so I have +1, -1, and then I'm left with H2. Okay, don't forget, hydrogen is diatomic, so when you have hydrogen left over, you will have to write it as H2. So go back and balance my reaction, a 2, a 2, and a 2. So I'm in good shape now. 2 sodiums, 2 sodiums, 2 hydrogens, 2 hydrogens, 2 fluorines, 2 fluorines. So let's look at one more of these. Let's look at magnesium plus HCl. So I need to ask myself, is magnesium reactive enough to replace the hydrogen in HCl? So in this case, I see that it is. Okay? Magnesium is more reactive than hydrogen. So my products would be MgCl plus H2. So magnesium is +2, chlorine's -1. So I cross my charges there. Put a 2 there to balance it, so I'm in good shape now. Let's go ahead and try one last one. Let's do HCl again. We can do plus silver. So I'm asking myself, is silver reactive enough to replace hydrogen? Okay? And you see from the activity series that it is not. Okay? So I could write no reaction, but let's say I forgot that step and I went ahead and wrote out the products. And I wrote AgCl plus H2, and then I realized where I had gone wrong. Okay? I caught myself. Don't need to scribble this out. I can just go back and put an X over the arrow, and that shows me the reaction does not happen. It's still valid to predict the products, just be sure you put that X to show that no reaction happens. Okay, so just be aware, one thing I didn't mention earlier, all these reactions I could have written flipped. I could have written FeCl2 plus Li. I could have written 2 plus NaF. Okay? So changing the order of the reactants changes nothing, okay? So don't be stuck looking for a certain form. You could see, Z plus XY, and it would still be the exact same thing, okay? So hopefully you would also notice that any of these reactions that actually happened, I can also look at in the reverse, okay? So if I look at them in the reverse, you would always have no reaction, because if calcium, in this example, is reactive enough to replace copper, then going backwards this way, copper would not be reactive enough to replace calcium. So keep that in mind. And so hopefully predicting the products of single replacement reactions will not be too difficult for you. Be sure you always go back and double check your charges. Be sure you make sure you balance the equation. But most importantly, for single replacement reactions, just ingrain this in your memory. When you see a single replacement reaction, go ahead and consult the activity series. Okay? So I think it's good practice to, when you see a reaction, you need to predict the product, go ahead and label it. Write a C beside it, write a SR beside it for single replacement. That way when you see single replacement or write single replacement, you'll know to immediately go and consult the activity series. And then don't be afraid to put no reaction as your answer. Okay? You'll see and you'll learn in chemistry, everything we mix together doesn't automatically react. Okay? So don't be scared to write that. Oftentimes that is the correct answer.